We want to find the curvature of the helix given by r of t at the point when t equals 0. We just did this problem using this formula for curvature. I thought we'd do this again, and this time use this formula to determine the curvature of the helix when t equals 0. We have the magnitude of the derivative of the unit tangent divided by the magnitude of r prime. And remember, when finding the curvature, we're determining the reciprocal of the radius of the circle of curvature. So here we see the graph of our space curve in purple. Again, notice how it's a helix. And if I pause this for a moment, this green vector is a unit tangent vector. And so at the initial point of this unit tangent vector here, this blue circle is a circle of curvature. And the curvature of the helix at this point would be the reciprocal of the radius of the circle of curvature, also referred to as the radius of curvature. And because we have a helix, notice how if we animate this circle of curvature, the circle doesn't change, which means the curvature of this helix is constant at any point on the curve. We'll begin by determining the unit tangent vectored valued function, t of t, which is equal to r prime of t divided by the magnitude of r prime of t. After we determine this vector valued function, we'll determine its derivative. So the x component of r prime of t would be the derivative of 2 cosine 3t. Notice how this is going to require the chain rule. So the derivative is going to be negative 2 sine 3t times 3, or negative 6 sine 3t. The y component would be the derivative of 2 sine 3t, which would be 2 cosine 3t times 3, or 6 cosine 3t. And the z component would be the derivative of 4t, which is 4. And now we want to divide by the magnitude of r prime of t, which should be equal to the square root of negative 6 sine 3t squared plus 6 cosine 3t squared plus 4 squared. Now let's take a closer look at the radicand, or this expression underneath the square root. If we square each of these, we would have 36 sine squared 3t plus 36 cosine squared 3t plus 16. Now looking at just these first two terms though, notice how if we factor out 36, we'd have 36 times the quantity sine squared 3t plus cosine squared 3t. Then of course we still have plus 16. But because sine squared theta plus cosine squared theta equals 1, notice how this simplifies very nicely to 1. So our radicand simplifies to just 36 plus 16, or 52. Which means we can write the unit tangent vectored valued function as 1 divided by the square root of 52 times the x component would just be negative 6 sine 3t. The y component again would be 6 cosine 3t. And the z component would just be 4. Again, notice how instead of leaving this in the denominator, I just put this as a fraction as 1 over the square root of 52. Now the square root of 52 does simplify to 2 square root of 13, but I'm going to go ahead and leave it in this form. Now for the next step, we'll find the derivative of this unit tangent vectored valued function. So now we'll find t prime of t, which is going to be equal to 1 divided by the square root of 52, and then the x component would be the derivative of negative 6 sine 3t, which would be negative 6 cosine 3t times 3, or negative 18. cosine 3t. The y component would be the derivative of 6 cosine 3t, which would be negative 6 sine 3t times 3, or negative 18 sine 3t. And the z component would just be the derivative of 4, which is 0. And because we're only trying to determine the curvature at t equals 0, let's now evaluate this at t equals 0. So t prime of 0 would be equal to 1 divided by the square root of 52 times, when t is 0, the x component would be negative 18 times cosine 0, that's negative 18. The y component would be negative 18 times sine 0, which is 0. So we have a y component of 0 and also a z component of 0. If we perform this scalar multiplication, we would have an x component of negative 18 divided by the square root of 52, and of course the y and z components would still be 0. So notice how to apply this formula. We would take the magnitude of this vector, t prime of 0, and divide by the magnitude of r prime of 0. Well, remember, here's r prime of t, so now let's find r prime of 0. R prime of 0 would have an x component of negative 6 times sine 0, which is 0, a y component of 6 times cosine 0, which is 6, and a z component of 4. Now that we have these two vectors, we can determine their magnitudes, then their quotient, to determine the curvature. Let's go ahead and do this on the next slide. The curvature at t equals 0, again, is equal to the magnitude of t prime of 0 divided by the magnitude of r prime of 0. So we would have the square root of negative 18 divided by the square root of 52 squared plus 0 squared plus 0 squared divided by the square root of 0 squared plus 6 squared plus 4 squared. And now we'll go to the calculator to approximate this value. So our numerator is going to be the square root, and then in parentheses we have negative 18 divided by the square root of 52, right arrow, close parenthesis, squared, right arrow, divided by our denominator, which should be the square root of 6 squared plus 4 squared. Right arrow, and now we can just press enter, and notice how the curvature is approximately 0.3462. Which again, going back to the graph, is equal to the reciprocal of the radius of this circle of curvature, which again does remain constant at any point on this helix. I do want to go back to our work just for a moment. One of the main reasons this process was fairly straightforward using this formula for curvature was because when we found the unit tangent vector valued function here, the magnitude of r prime of t here simplified very nicely. If it didn't simplify so nicely, and we had functions of t underneath the square root, it would have made determining t prime of t much more difficult. We would have had to apply the quotient rule in order to find the derivative of this vector valued function. But because it simplified so nicely, this was pretty straightforward. And again, our curvature was approximately 0.3462. If we go back to the first example, we did the same problem using this formula for curvature, which we see here, the process did take a little bit longer, but when t prime of t is difficult to determine, using this formula here is often much easier, even though it does require evaluating a 3 by 3 determinant, which is shown here using expansion by minors. And as we see here, of course, the result was the same when calculating the curvature. I hope you found this helpful.